This work presents real-time constraint-based planning and control of robotic manipulators for safe human-robot collaboration. We will show that the proposed methodology, a combination of a rapidly exploring random tree motion planner and the Explicit Reference Governor constraint control law, can let the robot reach target references while avoiding collisions with different static obstacle scenes and humans. And as such, we will improve the performance of a collaborative robot while certifying safety in cluttered and dynamic environments, which is a problem with the current collaborative robots. In recent years, many manufacturers have been facing the trend towards mass customization, for which they need an increased flexibility in their production environments. Therefore, they want to combine the strengths of humans and robots with the so-called collaborative robots. These robots work in constantly changing and cluttered environments and share their workspace with humans, so they must be safe. Though, currently these robots are made very slow to be safe, making them less productive and so less economically attractive. The goal of this work is to improve the robot performance with real-time control methods while certifying safety in cluttered and dynamic environments. To see which control strategy would be a good candidate solution to this problem, we have to know the main control design specifications. First, the control law should be computationally efficient. Then, in dynamic environments, reactive control methods are well suited. Mapping between joint and task space should be considered since set points and obstacles are mostly given in task space, whereas the robot states, inputs and dynamics are mostly considered in joint space. Thereby, we expect that the controller should be asymptotically stable and that global convergence should be ensured. And of course, we have to guarantee safety by enforcing the state and input constraints. We consider the following classes of constraints: actuator saturation or torque constraints, operating region or joint angle constraints, speed limitations, joint velocities and the Cartesian end-effector velocity, and obstacles like objects in the robot workspace or a human body can be approximated by spheres and cylinders, and walls can be used as a virtual fence between a robot and a human coworker. A few years ago, the Explicit Reference Governor was introduced. It is a control method with very limited computational requirements and so an attractive control scheme for robotics. This is also why we have chosen to work further on this ERG scheme for robotic manipulators. Let's start with the ERG algorithm for a robotic manipulator. The ERG ensures safety constraints by transforming the desired goal into a safe goal applied to a pre-stabilized system. First, we pre-stabilize the robot dynamics to an auxiliary reference by a classic PD controller with gravity compensation. This auxiliary reference is a feasible reference that can be safely applied to the pre-stabilized system so that the pre-stabilizing control layer does not have to account for any system constraints. Once we have a pre-stabilized system, we can add the ERG to account for the input and state constraints. Therefore, the ERG continuously manipulates the derivative of the applied reference, such that for a constant applied reference, the transient dynamics of the robot will never cause constraint violations. This is done by scaling the navigation field's direction with the dynamic safety margin's amplitude. The navigation field answers the question in which direction the applied reference should proceed, and the dynamic safety margin answers the question how safe it is to change the applied reference. The first vector, the output of the navigation field, is a vector that points from the applied reference to the desired reference. Therefore, we have to add an attraction field around the goal configuration. To repel the robot from steady-state inadmissible regions, for example obstacles, we have to add repulsion fields in the navigation field. In the picture, this is visualized by a repulsion field for a wall constraint. So the closer this applied reference V would come to the obstacle, the more it will feel the repulsion force from the obstacle, and as such it will move away from the obstacle. By adding the green attraction field and red repulsion field vectors, we get the total blue vector which represents the direction the applied reference has to follow. Thereby, the applied reference reaches the desired reference while avoiding the obstacle. However, only with this navigation field, we cannot guarantee that the robot will never collide with the obstacle, because it doesn't take into account the dynamics of the robot. The second factor, the output of the dynamic safety margin, is a scalar that represents the distance of the worst-case constraint to violation. We have implemented the trajectory-based dynamic safety margin, which means that we will predict the trajectory the robot will follow from its current state x towards the safe reference v. This prediction is visualized in purple. The minimal distance between this predicted trajectory and the obstacle is denoted by the scalar delta in blue. As long as the scalar delta is positive, the applied reference can be changed. The smaller the scalar, the slower the applied reference will change. When the scalar is 0, the applied reference is not allowed to be changed, since this could cause constraint violations in the future. References are mostly given for the robot end-effector in task space and as such should be transformed to joint space by inverse kinematics. In the experimental validations from our previous work, we have tracked the pose of the reference and of the dynamic obstacles with a Vicon motion capture system. Note that in these experiments, the perception, inverse kinematics and ERG work at 100 Hz, except the pre-stabilizing control layer, which works at 1 kHz since this is the rate at which commands should be sent to the robot. We can now take a look to a result we obtained with the trajectory-based ERG in our previous work. In this experiment, the robot follows the position and orientation of the wooden reference plate while avoiding the human's arm and head. Both the pose of the wooden plate as the human's arm and head are detected via a Vicon motion capture system. As you can see, the robot shows to be very reactive, fast and safe in these human-robot collaboration scenes with the trajectory-based ERG. However, the experiments in our previous work were all done in empty environments. Once the workspace becomes more cluttered and so more complex, a pure trajectory-based ERG will encounter problems with local minima because of the navigation field that is based on potential fields. So, what are these local minima problems? The applied reference will be attracted towards the desired reference but will also be repelled from the obstacle and as such will get stuck in front of the obstacle. This is because the repulsion field and the attraction field have the same size but work in opposite directions and cancel each other out. To solve this problem, we have combined the individual strengths of the Explicit Reference Governor, which guarantees constraint satisfaction in highly dynamic environments but often gets trapped in local minima, and the rapidly exploring random tree sampling-based motion planner, which can solve complex path planning problems in cluttered environments but has issues handling dynamic constraints. The rapidly exploring random tree, RRT, can solve path planning problems in more complex obstacle scenes. How does it work? Well, it grows a tree from the starting position, here the red dot, towards the goal position in yellow. Once one of the trees connects the starting position with the goal position, a path in between them is made and can be followed in the case that the environment doesn't change. However, it cannot handle dynamic obstacles since it takes too much time to compute one of these paths. And therefore we want to combine the Explicit Reference Governor with the rapidly exploring random tree. In this case, we still need the same pre-stabilized system and trajectory-based ERG as before. To combine a path planner with the ERG, we made a reference selector that sequentially assigns one of the waypoints generated by the planner as a target reference for the ERG. The path planner plans a path towards the target reference and thereby avoids the static obstacles in the environment. The reference selector receives this planned path from the planner and the auxiliary reference from the ERG and selects the kinematically safe waypoint. In this 2D visualization, the environment constraints are illustrated with black lines and a gray box. The target reference is visualized with a dark green circle, and the auxiliary reference from the ERG is represented with a light gray circle and a black dot in the center. At the start, the auxiliary reference is equal to the initial robot configuration. When the path planner receives the current robot configuration, the target reference and the obstacle data, it plans a path that is depicted with light green dots. Based on this information, the reference selector selects the first waypoint illustrated as an orange dot and sends it as a reference to the ERG. In the next step, the reference selector selects the next waypoint and checks if the kinematics of the current auxiliary reference, which in the meantime already moved in the direction of the first selected reference, violate the static obstacle constraints. This procedure is repeated at the rate of the reference selector. When no collisions are detected, we can always send a new candidate waypoint to the ERG. However, when a collision is detected in the prediction of the current auxiliary reference toward the candidate waypoint, the reference selector maintains the previously selected waypoint depicted in orange and keeps checking the next waypoint that is depicted in red. By repeating this strategy, the auxiliary reference will follow the blue path toward the reference position without getting stuck in local minima and will not violate any of the input and state constraints. In the following experimental validations, we employed an RGBD stereo camera to perceive the static obstacles and to track the human skeletons in the environment. Note that in the following experiments, the pre-stabilizing control layer works again at 1 kHz, the perception reference selector and the ERG work at 50 Hz, and the planner works at a lower rate of 1 Hz. First, we will show how the pure planner, the pure ERG, and the combination work in a quite simple primitive shaped obstacle scene. In this case, there is no real difference between the ERG and the RRT+ERG, since the obstacle scene is still quite simple, whereby the reference selector doesn't detect collisions and as such can give almost directly the last reference point from the planner. We can see that for most reference steps, the robot reaches the desired references faster in the ERG and RRT+ERG cases. Here you can see the RRT+ERG in case the robot is disturbed by a human. The shortest distance between the robot and the human is depicted with the orange line. Sometimes the robot will not move away from the human. This is when the applied reference would be pushed into a steady state inadmissible region, so at these moments the applied reference freezes to be safe. At other moments you can see that the robot is pushed away from the human and avoids the obstacles while avoiding contact with the human. It also works with multiple humans. However, note that the camera cannot detect the second human as good as the first, since the human's body is partly behind the wall and the robot. However, in a more complex primitive shaped obstacle scene, we will see that the ERG will get stuck in local minima. Here, in this more complex static environment, we can see that when we ask the robot to go to a reference inside a box, which we ask at 7 seconds and at 17 seconds, with the pure planner the robot can reach this reference position where the green path depicts the planned trajectory. With the pure ERG, we can see that the applied reference in blue gets stuck in local minima and as such doesn't reach the desired reference. We can also see that in the video, where the blue path denotes the trajectory generated by the applied reference. This is because there are repulsion fields that repel the robot from the sides of the box, and there is also an attraction field that attracts the robot into the box. but these two potential fields have opposite directions and cancel each other out. With the proposed RRT-ERG scheme, we can see that the robot can reach the target reference inside the box. Here you can see that the reference selector, visualized with the orange points, freezes the selected waypoint at moments it detects a collision, and as such can give better waypoints to the ERG. Here you can see them all together, and for almost all references we can conclude that the RRT-ERG let the robot move faster but still safely towards the target references. The biggest difference is that the RRT-ERG can also take into account all system constraints in real-time manner, which is not possible with the pure RRT Connect planner. Here we can see again a dynamic version of this experiment, but since this scene is more complex and more cluttered, the robot behavior is less dynamic since there are many steady-state inadmissible regions. Also, the overall dynamic safety margin is smaller because there are many obstacles nearby the robot. However, we can see that the robots can still reach the references while avoiding contact with the human and the obstacle scene. The previous scenes were modeled with primitive shapes. However, in some cases it might be better to transform the occupancy data to an octomap. For the last experiments, we transformed this static obstacle scene without a human to an octomap, a 3D occupancy grid map. The path planner can work with this type of data, but the ERG cannot. Therefore, we introduced the octopoints concept. In this video, you can see how the pink octopoints are generated when manually moving the robot. Since we could only gather the collision points between the robot and the octomap, we enlarged or padded the robot with different padding radii and checked for collisions between these padded robots and the octomap. Every time a collision is detected, an octopoint is generated, and after a while we remove the oldest octopoints out of the list. The purple arrow denotes the shortest distance between the robot and all the octopoints. This video shows how the robot can reach a reference behind the small Now robot and return to its initial configuration with the RRT path planner. In this video, you can see that the ERG has problems with these two references because it gets stuck in local minima in front of this small robot and then also cannot move back to its initial configuration. In this video, you can see that the reference selector can provide extra waypoints and freezes them as you see here, such that the applied reference coming from the ERG cannot get stuck in local minima. And here you can see them all together. And again we can conclude that the RRT-ERG proposed framework let the robot reach fast and safe the target reference poses. Note that the computational time of the ERG is much smaller than that of the RRT planner. For the last, most complex obstacle scene, which are experimental validations 3 and 6, the ERG needs 10 milliseconds, whereas the RRT planner needs more than 100 milliseconds. The ERG has the highest computational time, around 30 milliseconds, for experiments 2 and 5, which are the validations in the more complex primitive-shaped obstacle scene. This is because the move-its collision checking algorithm is employed to compute the distance and the direction between the robot and the nearest obstacles. And finally, we can see that the robot can also avoid humans in this scene. In conclusion, the proposed framework improves the performance of a collaborative robot while certifying safety in cluttered and dynamic environments.